Good afternoon, everyone. So we'll start today's session. I am Simran and I will be solving today week 3 related problems. So we'll solve some problems, then we'll do some MATLAB or simulation to see how those problem if we can solve this problem in this software. So let us start. Okay. So this is the first question. Okay. So the question is that these are two block diagrams of a control system, and this is the input RS and there is this output CS. Now these are the subsystems in this whole system, and this is the whole system here. So the as we know that transfer function is not unique for a system, so different like many systems can have same transfer function. Therefore, for these two systems we have to find this Z, which is unknown transfer function of this subsystem, such that transfer function of these two are same. Now, what is the transfer function of first one? If we see first system, this is R. So since these two are in cascade, so these two will be just multiplied because this is in S domain. We can say Laplace domain. So this is Z. This R is input to this system and Y is the output. Now the transfer function of this system, which is, sorry, this is Y, this is represented as C. C of S by R of S is Z by S plus 2. For second system, if we find the transfer function, we can see this branch and this one are in parallel because the output of these two are going to, suppose this is a unity gain kind of. So sum of, because these are in parallel and summing, the output is summing. So we can say the transfer function is 2s by s plus 2 plus 1. And this is the overall block. Now what will be the transfer function of second one? I'll simplify this one. So 3s plus 2 by s plus 2. Since the transfer function of this first system and second system has to be same, so from here we can see it is obvious that this z should be equal to 3s plus 2. So we have got the answer for this. This is a simple block diagram related concept because this we have, like, you must have studied in the third week. Now we'll proceed to second question. So in this one, the transfer function Cs by R2S. So if you see this block diagram, there are two inputs, R1 and R2, or you can say reference to the control block, and output is CS. So we have to find the transfer function when the input is this one and output is this one, is for this input output thing. So that means this has to be set to 0. Now if this is set to 0, obviously this is going to be 0 and this is also going to, because this is just the output is just multiplication of R1 by G2. So G2 R1 is 0 and this is also 0. So what is left? This will be reduced to this one. We have G4. Input is going to a summing block. There is R2. So I am not using this subscript S tends to. This is in lab S domain. So we'll just use this notation. This is going to H1, which is in feedback path. So this is the forward path from input to output. The direct path is the forward path, and this one, which is going from output to input side, that is the feedback path. This is S2, and this is going to a summing block. Here it is minus, this is plus. But there is no input, only single input, so the plus has no meaning. This is the thing. Now, this is the output, CS. So what we can see, if we see this is the input, this is the forward path, and this is the output that we are getting. Now this whole thing is in feedback path. So how can we simplify this? This is R2. There is a summing block, and it is having positive sign. Then we have G3, and the output is P of S. Now in feedback path, we have H1. So we have a feedback block. There is H1, then H2, and here we have minus. So it is multiplied by, we can say, if this is the signal X, then the coming out of this will be H2, H1X, and here what we are getting is minus H2, H1X. So now this is going to G4, and this will be minus, and this is the feedback. Okay, so now we can apply the feedback closed loop formula. For this case, either we can keep it like this and we say that, okay, this is a positive feedback, or simply what we'll do, we'll just extract this negative sign and we can say, okay, this is R, this is a summing point. We have this block G3 with output C. This is a feedback path G2, sorry, G4, no? Okay. G4, H2, H1, and this is minus. So this is one simplification of this. Now let us apply this formula. What will be the closed loop transfer function? This will be the gain in forward path, that is G3 by 1. Since this is positive feedback, so it is minus, and then we'll have multiplication of forward path gain and feedback path gain. So G3 minus G4 H2 H1. This gives Is it different, or we have forward paths and backward path gain also? Okay, loop gain we have, no? Okay, simply remove this one. We'll start with the negative one. This is G3. So 1, 3, G4, S2, S1. And for this one also we got same, because this is G3, 1 minus G3, G4, S2, H1. So this is G3 by 1 plus G3, G4, S2, H1. Okay, so this is the answer. Now let us proceed to third question. This is related to signal flow graph. Now this block diagram simplification that we have done, sometimes it can be messy or we can forget some signs and all those things. So there this thing is useful. So here if you see in block diagram, we are representing signal by these arrows and system by these blocks. In signal flow graph, we have signals as nodes and this arrows as the system gain, you can say. So we have to apply Mason's gain formula and find the transfer function. Now if we try to find the transfer function, so this will be summation I equal 1 to n, then pi delta I by delta. Okay, so here n is the number of forward path. If we see here, there is only one forward path from input to output, this one. So n is equal to 1. What is P? P is, so means the formula will reduce to what? This will be P1 delta 1 by delta. Okay. So what will be the P1? P1 is the forward path gain. So this is the forward path. What is the gain of this? This is 1 unity, not negative. So we have 1 into G1 into G2, G3, G4 and into 1. So this is simply G1, G2, G3, G4. Fine. Now we have to find delta. So delta will be 1 minus. We have to see what are the loops, like feedback loops. So this is the one loop that we are having. This is second one. And if you see, this one is also a loop. And this whole one is also a loop. So there are 4 loops. L1 is -1. L2 is -1. Then L3 is this one. No? This is -2 G3 G4. And we have L4, which is -2 G2 G3 G4. Okay, these are individual loops. So we'll have L1 plus L2 plus L3 plus L4. And then summation with gain for non-touching loops. So what will be this? This loop is touching with this one, the bigger one loop, but not touching with this loop. So we'll have L5, which is minus 1 into, or we can say L1 into, this one is L3, and L6 is L1 into L2. So we'll have 2 G3 G4 plus 1. So what is delta? 1 minus minus 1 minus 1 minus 2 G3 G4 plus 1 plus 2 G3 G4. Okay, so this is 1 plus 2 plus 2 G3 G4 plus 2 this gives us 4 plus 4 G3 G4 and then okay, so this is your delta. Now we have to find delta 1. So delta 1 will be what? This is simply the loop, like 1 minus whatever loop is not touching to this forward pass. So we can see all the feedback loops are passing through. Means if we remove these branches, this in forward path and nodes, then these loops will not exist. Means because they require this path, or we can say node. Therefore, that will be simply 1. So final transfer function will be G1, G2, G3, G4 by what we found is 4 plus 4 G3, G4 plus 2 G2, G3, G4. Let us see. This is the correct answer. So we have got the answer. Okay, any doubt in this question? Otherwise, we'll move to next one. Fine. Now, this is the fourth question. Question is that a system is known to have type less than or equal to 1. So what do you mean by type? And which of following is possible? So what do we mean by type is number of poles at origin. So if GS is a transfer function and it has S minus Zi, I equal to some value, I1 to M, and then product J equal to 1 to N, S minus Pi, Pi's are pole, then here we may have S to the power N. So this N is the type. We can define type of system by this order of the poles at origin. So it says that system has type less than or equal to 1. That means either it's 0 or 1. And then we have to comment about this, that which one is correct. Now if it is 0, then what will be the GS? GS will be simply this multiplication by, because S to the power 0 is equal to 1. This is for type 0. For type 1, we have GS equal to this one. So we have one pole at origin. Now these are the systems. System can be any of these. So now we have to find the error constants. So how will we find? So suppose we apply a unit step function. So what will be the error for this unity feedback case? This will be delete it. Okay. So we have this, and for Kp we know it is simply 1 by 1 plus g of 0, or we can say limit s tends to 0. So this is 1 by 1 plus g of 0. And for kv is limit s tends to 0 s into gs. This is for kp and this is for kv. Okay, fine. Let us see the type 0 system. So if this is the system and we are trying to find kp. So this will be 1 by 1 plus g of 0. So we'll just simply put 0 in the place of s. We'll get some constant. So the kp value, that will be 1 plus some constant. That means for type 0 system, we'll have kp as constant. Now if we try to find kv, so this will be, for type 0 system, this will be s into pi. Limit s tends to 0. This is a kv. So if we apply s equal to 0, then this will be simply 0 because this will go to 0. So one thing is that we have found kp is constant and kv is 0. So this is for type 0 system. Now if we see type 1 system, so what will be the value of kp? This is 1 plus g of 0, where s is equal to 0. So if we put s equal to 0, then this will shoot up to infinity. So kp will be infinity. And if we try to find out kv, so this will be s into s minus pi. So this will cancel out, limit s tends to 0. This will be, so this is some constant c. So for type 1 system, what we have? We have kp going to infinity and kv is a constant. Because we know now for type 1 system, if we apply a step input, then it will track that one. So obviously the error will be 0. Now if error will be 0, so error is simply 1 by kp, so kp should go to infinity. Okay, so these are the correct comments that we can tell about this system. Any doubt in this question? Okay, proceed to next one then. So this question says, assume RT equal to 0.5 T. Now we were saying R, this is the input, and all we were seeing up to now was in the Laplace domain. So now we have come to, this description says that RT is a signal which has Laplace transform RS. So now just leave the information about this. So there is a signal RT which is equal to 0.5 T. So it's some kind of a ramp signal. So with increasing T, it is increasing. This is the RT. And it is desired that ESS is less than equal to 0 for system with unity feedback. So this is the system with G. That is a summing point. This is the RT. This is the feedback. This signal is the error, which is RT minus, this is output YT. So it says, now for this error, what we know that this is the time domain representation. So obviously, if we do the Laplace domain, so this will be, if you see, this we can represent as E of S equal to R of S minus Y of S. Now R of S is value that is being given, and output Y of S is G of ES. So we have 1 plus G. So this is the Laplace transform of error. Now we have to find ESS, that means a steady state error. So when time like transient response die, so that we can find ESS is, we'll apply simply final value theorem, limit S tends to 0 as ES. So this will be limit S tending to 0 as RS by 1 plus G. Okay. So this is how we can find ES. Now it is saying that this ESS should be less than equal to 0.1. So we have to find the value of K for this as, so that this is satisfied. Okay. So what we'll do for RS, what can we substitute? We know RS is 0.5 T. So what will be Laplace transform of this one? 0.5 by S square. So this will be 0.5 by S square. Which is E of S by 1 plus, and what is the value of G? This is K by S plus 50. S plus 50. So this is what we'll get. This is what we'll get. Okay, this will cancel with this one. This will go to denominator. Oh, no. Now we have to apply limit. So ESS is limit S tending to 0, 0.5 S plus K by S plus 50. So what we get? This is 0.5 by K by 50, because this will go to 0 and this will go to 0. Okay. Now what has to be satisfied? That this error is less than equal to 0.1. So this will be what? So K will be greater than 0.5 into 50 by 0.1. So this will be 250. So K is greater than equal to 250. Okay. There are various options, but this is the correct one to get this ESS less than equal to 0.1. Now let us see how we can do this in simulation. So Let me just open one more. Okay, have you all are you all familiar with MATLAB? Yes, Vamsi, you have raised your hand. No, this is third class of. Okay, fine. So, this I think you will be having access to MATLAB through this course, as far I know. So, here you have this graphical simulation tool, which is Simulink. So, there, what you can say, this is a block diagram based simulation platform. So you make different control system blocks and all, and you try to simulate that to see whether, like, to do analysis related to whatever you are working and all. So we'll try to see, means analyze this question. Analyze means basically whatever we have derived theoretically, whether it is correct or not. So for this, what is a block diagram representation? This one. So we'll try to make this block diagram. Now in Simulink, what we can do, we can simulate different system. Basically, there are various plant like mass spring damper system and this RLC circuits. So many of the times we'll just try to analyze the behavior of the system, and will not be doing, like, will not be actually giving a step input to mass spring damper system or this RLC circuit or any you can say robot or vehicle. There are various systems, so we cannot give input. So what we do, we try to simulate this first. So in software, what we do, we have this mathematical model of that system, and we try to simulate that in software. Then once that is done, then we try, means the other way is to have some hardware which you emulates that behavior. I mean, that copy that behavior. So we call that emulation or something, but we'll be doing here simulation. Now what we'll do, we have to make this block diagram. So we have this transfer function G. Let us find the transfer function. So this is the library browser. Here we can find different blocks like sources, components and all. Then if you want to see some signals, so here in maybe in electrical we have this oscilloscope and all those things. Then uh, uh, once these are the hardware instrument to see the signals. So here we'll be having a scopes and all. So what we'll try to find is transfer function. Now, so all the analysis that we are doing in S domain, you can see, and these are for continuous time signal. So we'll have a transfer function which is in continuous domain. So these all transfer function with Z domain, or we can say Z variable. These are discrete time transfer function we are dealing with. So we have added this. This is one way of uh, bringing the library blocks to the SLX file. Or what we can do is simply, suppose we delete this, we'll just double click this one and we'll write transfer function. Here, see, and this will bring the transfer function. Now, what is the transfer function? K by S plus 50. What is the value that we have found? This is 250. Okay, so let us put the values. This is 250, and in the below, if we simplify this, this is s square plus 50s plus 0. So denominator term will be s square plus 50s plus 0. Okay, let me expand this so that you can see the transfer function. Fine. Now this is a unity feedback system and we have ramp input. What we need extra? Summing block. So we need a sum block. This will give input to this one. We have a feedback which is going from here to here. Fine. And then this is a negative feedback. Okay. Have a source which is ramp. Slope is 0.5. And its start time is 0, means at 0 second start. And initial value is 0. Fine, but we are not concerned with this thing. We are concerned with the steady state. So at final, what is the value that we want to see? Now we want to see the result. So what we'll have? We'll have a display that will use a scope. We have to see what is the error. I mean, the error is less than 0.01, no? 0.1, sorry. Okay. So we'll use a mux. Mux is basically to concatenate the signals. So this is one signal, which is the output. Let us name this so that we can have a proper visualization. And this is the input signal. This is R. Okay. So let us use a value greater than 250 now. So we can use 270 maybe. Okay. Let us simulate this. I hope this is visible. Okay. So here you can see this is the R, which is the yellow one, and Y is the output. And we can see the transient also, that, and let me decrease the time. 5 seconds, we'll do simulation for that. Can you see the transient here? It is not like a straight line with some slope. It is having some exponential type of thing. Then it is set like at a stereo state, there is difference between this reference and the output. What we have to check? This value. Okay. So at a particular time, let's suppose at this time. Is there some cursor? I think we have cursor. Fine, I don't know how to use this one. So let us see the plot on now. We will be able to do this. Okay, what we can see that at this point, what is the value? That is something 1.9 something, we can say. Or let us take this point, this crossing, which is crossing the vertical axis. So this yellow line is passing through this one and it has value 2. And this one is having value something greater than 1.9 at this time instant 4. So at time instant t equal to 4 seconds, this output, which is in blue color, this has value 1.91, I think. Yeah, suppose. And then this has value 2. So this difference is less than 0.1, obviously. Now with if we increase it more, then this will decrease more. So that we can see, but let us take some smaller value so that we can see what is the response. So what is expected? What we have seen that for ESS less than equal to 1, what should be the condition? This K should be greater than 250. Now we have taken a value less than 250. So what we expect from theoretical analysis, we have seen ESS will be greater than 0.1 for value K less than 250. So we can see the error is very large compared to earlier one. Is this clear? Okay, we'll move to next question then. This is the next question. In the system shown in the figure, so this is a unity feedback closed loop system. And what is the question asking? That what should be the value of K and A to obtain a steady state error of 0.5 for unit step input? So this RS is 1 by S because this is a unit step input, and it is asking that ESS should be 0.5. Okay. So this is a unity feedback system, and here what is the forward path transfer function? That is K by S to the power A S plus 20. Now what we want that the error should be, there should be non-zero value of error when input is unit step. Now if we are giving, this is kind of internal model principle, that suppose we have some dynamics of input and we want that to be tracked. So for this system, this closed loop system, the forward path should have that dynamics. Okay, that means suppose this RS is unit step and it has 1 by S. So unit step is 1 by S. That means if this whole system has to track this input, then in forward path, it should have at least 1 by S. Similarly, if it is ramp, then this is S square. So forward path should have S square. If it is less than this, that means if it doesn't have this poles at 0 of order 2 and it has just 1 by S, then there will be error. Similarly, if the input is suppose sine wave, that has to be tracked. So in forward path, it should have this dynamics. And this is what you have seen in the error analysis of the closed loop unity feedback closed loop system, that for unit step, what is the error value? This is 1 by 1 plus g of 0. Okay. Now if s is equal to 1, or you can say it's not equal to 0, then this will simply suit to, this will be what? 1 plus k by s plus 20. So what will be the value? 1 by 1 plus infinity. That means 0. So error will tend to 0. So that means we can't afford to have a pole at origin. A should be 0. Then only if we try to find the ESS, we'll have okay, remove the limit, it is simply k by s plus 20. So this will go to 0 and then we'll have 1 by k plus 20. So this will be the error when a is equal to 0. That means there is no pole at origin in forward path. So this is what we expect. So a will be 0. Now it is said that steady state error is 0.5. So what is the value of k? We have found a steady state value. This is 1 by 1 plus k by 20. This is equal to 0.5. So what will be the value of k? Let us simplify this. This is 1 by 0.5. So 2. This will be 2, no? K by 20 equal to 1. This implies k equal to 20. So the answer is k equal to 20 and a equal to 0. This is the answer. So what we expect when k equal to 20 and a equal to 0, then output will be having a steady state error which is 0.5 with respect to the input. So let us see this in simulation again. We can analyze this one also. What is the block diagram for this one? We have in numerator we have 1 and then it's s by 20. Oh, sorry, not coefficient of s. Okay. So this will be 1 and 20. Yes. Anand Teja, can you mute yourself? Okay, fine. Fine. Okay. So what we are trying to see the behavior of this system. So we have this transfer function 1 by s plus 20. Then we have found k equal to 20 and s to the power a. So a is simply 0. That means we simply have a gain that is a constant. So we'll use this gain which is 20. Okay. Now what is the input? Input is a step function. So we'll replace this ramp and we'll have a step function. So we'll apply this input. Now what it says that step time is 1, means after 1 second a step will start, that it will change value from initial to final. Initially it is 0 and final is 1. So this is a unit step function. Again, so we have to see output and input. What is the value? We have simulated the system. Let us see the response. So this yellow one is the input, which is the step. It is changing its value from 0 to 1 at 1 second. And this blue one is the response. So you can see the value of this one is 0.5. And then the error at the steady state, when the transient dies, it is 1 minus this 0.5, which is 0.5. This is what we expected. And this is what we have shown from the theoretical analysis. Okay. Now, this is what we said, no? So if we have the same dynamics as RS, that is unit step in forward path, then what do we expect? That there should be no steady state error. So now if we apply a integrator in this path, suppose this 1 by s here, So what we expect that there is no error. Let us do this also and see what happens. Hit this. And then we have an integrator. Fine. This is going to this. Okay. So there is little error. Let us increase the time. This is taking large time to settle. So here you can see in this portion when transient dies out, there is this no error. Okay. So if we apply suppose sine wave, there's some source like sine. Okay, fine. We can do this analysis later also. So is there any doubt in this question? We have used the theory that we have studied and then we are verifying this using the simulation. So this is about steady state errors. Now different type of like time domain analysis of system you have studied. So mainly the two types of system that you have studied is first order and second order system. So if we see this second order system, this is a second order system. So there are some statement about this and we have to verify whether it is correct or not. So whether it is over damped, under damped. So obviously I expect you that you have gone through lectures and you know what do you mean by over damped system and under damped. So if the input is a step input, then output is under damped. That means there will be oscillatory and then it will settle after some time. And if it is undamped or then it is simply okay. So if it is undamped, that means it will have oscillations. For critically damped, it will try to reach this one as soon as possible. And for over damped, this is a sluggish system. Output is very delayed and take times to reach the reference. So we have to find which option is correct. Now for the system, what is the transfer function? This is ys by rs, which is 100 by s square plus as plus 100. We know we can relate this with second order system equation. So that is omega n square by s square plus 2 zeta omega n s plus omega n square. Second order system. Now here omega n is the natural frequency of the system and zeta is a damping factor. So let us relate this. So from here what we get, this omega n squared is 100. So that means natural frequency of the system is 10 radian per second. Okay. So from there, if we try to relate this second coefficient, so 2 zeta omega n is equal to A. That means zeta equal to A by 20. Now the different cases are related to variation of zeta. So it's like if we see poles of this one, or you can say this one, so it's minus zeta omega n plus minus j omega n root under 1 minus zeta square. So if we see the S plane, that is sigma j omega plane, where are the roots? It depends on the value of zeta. Suppose this is a circle with omega and radius. This is zeta omega n. And this is omega n root under 1 minus zeta square. So j, because this is a j omega axis. Okay, so there are two poles here and here. And this is the case when it is under damped. When it is over damped, that means for this case, zeta is greater than 0 and less than equal to 1. Now, if zeta is equal to 0, that means S12 is simply plus minus j omega n. So it lies here in the S plane. So this is corresponding to these two, zeta equal to 0. If zeta is equal to 1, in this case, this will be what? Minus omega n plus minus. So it at this point. So at this point, there are two poles. This corresponds to zeta equal to 1. And there are two poles on real axis that corresponds to zeta greater than 1. Now we have to see. So obviously we know that this is underdamped, overdamped, all those things. So what we can see, zeta is a by 20. So that means if it is equal to 1, then a should be equal to 20. If it is greater than equal to 1, then a should be greater than equal to 20. That means this is not equal to, because these are separate case. Equal to is critically damped and greater than is the overdamped response. So this is better than. Okay. And for less than 1, theta greater than 0, what should be the value? A less than 20 and a should not be equal to 0. For zeta equal to 0, a should be equal to 0. So from here we can say, is it overdamped for a equal to 20? No, we found that this is critical damped for a equal to 20. So this is correct. Is this underdamped for a equal to a greater than 20? So for underdamped condition, zeta is between 0 to 1. And we found for this condition, a is less than 20. So that means for underdamped system, a is less than 20. This is correct. This is not correct. For overdamped system, a is equal to 50. So for overdamped system, what we found? That a should be greater than 20. No, why this sign is no? Okay, I have not deleted this equality. Fine. So a could be any value greater than 20. So that means it can have 50 as a value. Now this is what we have seen. So we'll verify this with simulation again. So let us simulate this system. So we'll have a transfer function. And this is a second order system. 100 by s square. And a value will vary 20, less than 20 and 50. Fine, or we can say simply 20, less than 20, greater than 20. So this is 100 s square then 20s, then 100. Okay, so what is the transfer function? This one. We'll apply input, which is unit step. Let us see what is the response. What is the output? This will be the output now. Now see, the input is going to this plant, same input that is going to this one, and the output is this one. So we are visualizing these two. What are we seeing? That can be made more bold or what? Hmm. I have to check how to do setting for this one. Fine. We can see that this is the input, this R, and the output is blue one, which is reaching this value after transient and setting at this point. This is for A equal to 20. Now, if we apply A greater than 20, so let us see for 50. What do we expect from here? So for A greater than 20, zeta is greater than 1. That means this is a overdamped system. What is this? Sluggish response. So let us simulate this one. Now it is taking more time. Earlier it was settling in 2 seconds. So we can see it more precisely. So this is 3 seconds. Let us increase this and make it 100. So you can see now it is settling at approximately 5.5 seconds. So from this we have verified that for A greater than 20, this is a overdamped system. Now if we consider A less than 20, so what it should be? This should be a underdamped system. Consider 10. See, there is this oscillations and then it is settling. Okay. If we keep it 0.1 approximately, that means A is approximately near to 0, because for undamped system, what we saw, zeta should be 0. That means A is equal to 0. So if A is near to 0, then there should be oscillations. If it is 0, there will be sustained oscillation. If it is near to 0, but some value greater than that, that means there will be oscillation and it will die after long time. Let us see. Okay, the value is decreasing, the amplitude of oscillations, it is taking more time. So that means 10 seconds is not sufficient. So let us take 20 seconds. Let us see if this is also not sufficient. Okay, so you can see the magnitude of this oscillation is decreasing. So this is a underdamped system because we are getting this type of output to unit step input. Okay, any doubt in this question? So you can try all these online also. I think Simulink online is available, so you can do that analysis by yourself also. Okay, so this is the next question. Consider two responses yn and y2. Y1 is the dashed one. This is the response. What is the input? This is a unit step. This is the input. And it is being applied at 0 second. This one is the output 1, and this is the second output of the system. What is given? It has damping ratio zeta1 and zeta2. Assume that natural frequency of system is L. So there are two systems. One is omega n square s square plus 2 zeta1 omega n s plus omega n square. Okay. And if it is this unit step is given to this system, output is y1. The second system is same, is having same natural frequency, but zeta is varying. This is zeta2 omega ns plus omega n square. Same input step, output is y2t. So same type of system, only zeta is varying, and there are two responses. So it is asked what is the value of, like, what can we tell about zeta? So we can see that this is the input and this is kind of response that we saw for overdamped system. Just now we did simulation and we saw that for theoretical analysis also, that if zeta is greater than 1, then it has this kind of response, first order system type of response. And there is this oscillation which is decaying. So this one corresponds to underdamped system. This is for underdamped system. This is for overdamped. Okay, so for underdamped system, zeta is between 0 to 1, and for overdamped, zeta is greater than 1. So this is zeta 1, no? Because this is y1, and this is zeta 2. So zeta 2 is greater than 1, and zeta 2 is less than 1, greater than 0. This is the correct answer. Any doubt in this question? Okay, fine. So we'll move to next question. So there are these 4 questions. All are related to same block diagram. There is this input. This is a forward path block, and this is the feedback path block. And this is a negative feedback control system. So it is asked that what is the natural frequency of this system, this whole system. Okay, this closed loop system. So for natural frequency, we have to find, that means this system may have this significant poles such that it can be approximated by second order system. So let us find a closed loop transfer function. If we find a closed loop transfer function, which shows the characteristic of this closed loop system. This will be 16 by s plus 0.8 by 1 plus 16 by s plus 0.8 into 1 plus as. That's fine. So this is 16 by s plus 0.8 plus 16, 1 plus as. S square plus 16a plus 0.8 s plus 0.8. No, not 0.8, it's 16. So now we can compare this to a second order system. So we have seen the dynamics of this second order system. This is omega n square by s square plus 2 zeta omega n s plus omega n square. So what will be the natural frequency? This will be root under 16. That means 4 radian per second. So this is the answer. Now we have to determine the value of A such that damping ratio of closed loop system is 0.5. Damping ratio. So that means zeta should be 0.5. Here we can see this should be equal to 16A plus 0.8 should be equal to 2 zeta omega n. Omega 1 is equal to 4. That means 8 zeta. And zeta is 0.5. It is said that zeta should be 0.5. So what will be this? This will be 4. So 16A equal to 4 minus 0.8. That's 3.2. This implies A is 0.2. So this is the answer, 0.2. Now in this system, we know all the parameters. We know the natural frequency. Obviously, this is characteristic system. But for overall system design, we know that A is equal to 0.2. Now what is said? We have to find the rise time. And we have to find the maximum percentage overshoot. So we can write the theoretical formula and we can do this. And one thing is that we'll verify it through simulation. Okay. So let us do it through simulation first, then we'll see, because we just have to apply a formula. What is the system? In the forward path, this is forward path. The system that we are having is 16 by s square plus 0.8 s plus 0. Okay. In the feedback, we have 1 plus 0.2 as. So we'll use a transfer function. Okay. So this is not required. This will go as output. Now this is 1 plus 0.2 s plus 1, and this one is 0. You can say simply 0. Let us see. it says that the given transfer function is improper transfer function, that the order of transfer function numerator must be less than equal to order of denominator. So this is one thing that we know, that for physically realizable systems, number of poles, or we can say order of denominator, should always be greater than or equal to number of zeros. So that means we cannot realize this transfer function. So what we can do, this is kind of differentiator, means there is a zeros that is being added. So what we can do, that we can add a low pass filter along with this. So we'll have, here we have 1 plus as, so we'll have some s plus some tau. I mean, we can say a low pass filter. How do we represent? That will be, so it will have poles at 1 by tau, and then it will decay like this. So this will be 1 by tau. So you know that this is a unity bandwidth. So it will be like this. This will be 1 by tau. Now this is a differentiator, so it amplifies noise. So what we try to do, we'll make this as small as possible so that it passes only low frequency signal. That means DC signal. For our case, this will be low frequency signal. And we have to add it such that there is no amplification or attenuation of the signal in the path. So this transfer function, if we apply the DC gain, so what will be the DC gain? Simply, if this is g of s, so g of 0, that is tau by tau, because h will tend to 0, so this is 1. So gain is 1. That means if we give this system here gs, and then we apply the signal there, then it will simply low pass the signal, means high frequency signal will be attenuated and low frequency signal will pass, and this will go to this block. So now if we combine these two, then it will get a form of proper transfer function, that will be 1 by as into tau by s plus tau. So now we can see the order of numerator, which is 1, and order of denominator is 1. So now this is realizable. So we will use this transfer function. So we have to keep this small. So suppose we'll take tau equal to 1000. So it will be 0.00 some radian. So it will be very small frequency. So this is a 0.2 s plus 1 multiplied by tau, that is 1000. And then we have s 1s plus 1000. Okay, now this is realizable. Let's keep it 10 seconds so that we can see the transient involved. I think it is visible. Now what we have to do, so here you can see that we know the system parameters. Now the question is to, and we have found out that if a 0.2, zeta is 0.5, so that is between 0 to 1. That means we expect that output will be underdamped. So we can see from the output response that there is this oscillation and this is settling. Okay. The next question is to find the rise time. So for rise time, what we do, we find the time duration in which output reaches from 0 to 100% for first time. So it is at 0 at this time, and then it reaches 100% of the input at this time. So if you see from here, it is approximately 0.6. We can zoom it and see it. And this is starting at 1 and this is 1.6 at which it is crossing the unit step input. So this is 1.6 minus 1, that is 0.6. So what do we expect the rise time to be? That is 0.6. So approximately, yes. So we are getting this from the simulation. Now we have to see what is the percentage overshoot. So percentage overshoot is like y at Tp minus y at when steady state reaches by steady state value into 100%. This is a percentage overshoot. Okay. So we'll try to do this. We'll find it. So from there, we cannot find the percentage because we have value. So if we see this yTp minus y infinity by y infinity, we can find out. Then from there, we can calculate this one. Let us see what is the value. This is approximately 1.16. Because this is 1.15 and 1.12, so approximately this one is this. And the infinity at infinity settles to 1. So that means 1.16 minus 1 by 1. So 0.16. This is the overshoot. And if we say percentage overshoot, so it will be multiplied by 100. And this will be 16% approx. So this is the value. That is the answer. So from simulation, we can find out what is the percentage, like peak overshoot and rising time and then settling time, all those specifications that we use to design a control system that we can find out. This is from simulation. Now for theory, from theory, we have this formula of rise time. What is the formula? What is the formula of rise time? Tell me. I don't remember. I think this pi minus cos inverse zeta by omega and root minus zeta square. And for peak overshoot, it is e to the power minus pi zeta by root under 1 minus zeta square into 100. So you will simply put this values zeta and omega n because we know this value, and so you will see that you will find these values on. So this is about this question. Any doubt in this question? Okay, fine. So I think this is mostly clear to you all. that this third week course content related to time domain analysis of system and block diagram and signal flow graph representation of system. So if you have any doubt related to last two sessions also, you can ask. Is the assignment 3 due date over? So we have discussed about week 3. Yes. Reverse stability for bounded input, unbounded output. What do you mean by all the like what you I couldn't understand. Why this function is not realizable? Okay, I think I have turned off your mic or what? Okay, so it can be seen as that if you just have numerator like order greater than denominator, that means number of zeros greater than number of poles. Or you can say suppose simply s. So you have a transfer function which is s. Now in it kinds of a derivative. So it differentiates the input and gives the output. So that means it is when we say derivative, what do you mean? Y of k plus 1. Suppose y is the input. So y of k plus 1 minus y of k by delta t. So it is taking earlier like a value of y which is in future time. Okay. So if you see normal system, those are causal system. So until unless you apply input, you are not going to see the output. There will be some delay, then you see the output. Therefore, like physical systems are not like this that will having transfer function with numerator greater than this one, because we cannot have future value of output before applying input. Okay. How to install MATLAB? So I think there you have been provided, no? Let me see. So someone asks about MATLAB. MATLAB access. Thanks for, please let know if we are able to instructions. I think you have to create one. Okay, so you can follow these steps. Go to MathWorks, register there. I think this step you can follow because I already have this institute ID, no, so I can access. But since you are doing through NPTEL, so there will be some extra step. So you can follow this one. I think this you can see, no? Go to ask a question and go to the first mail, the earlier one. So there you can find that there is this mail by Suraj Kumar. And here, if you click on this link, you will get the instructions. Okay. Fine. Okay, for third order system, generally what happens for higher order system, we don't bother much because the poles, like we will having three poles. So we consider that two poles are dominant, means that will dominate the transient response. So suppose that there is a pole at s equal to 10 and there is a pole at s equal to 100. So obviously what will be the transient response? This will be some initial value. Yt will be equal to y naught, which is some initial perturbation, e to the power minus t by 10. Okay, so pole is at 10 and minus 10 and minus 100. And y0 plus e to the minus t by 100. So this will be the transient response of the system. Now if we see the transient response, okay, so this is for two poles. One will die very fast and other will take time to die, this transient response, because this is time constant 10 and this is 100. So one having pole at 100, it will have very small time and it will die within that, and this will take last time. So similarly for higher order system, we'll say like this is for second order system, no? So if you see overdamped system, there is one case in overdamped system because we say that okay, on S plane there are two poles. Let me draw the S plane. So we have two poles, one is here and one is very far. Now in this case we can say this pole has very negligible effect and will have effect from this pole. So the response that we get for unit step, that will be like a first order system. So that means that second order system is approximated by a first order system. Similarly, for higher order system, what we can say that two poles which are close to origin, that will dominate the signal, like transient response of the system. So we'll say, okay, these two poles dominates the system and this third pole has no effect. So we can approximate that higher order system with second order system. We can talk about this oscillations and all this. Okay, I think you have no doubt in all those things now. So okay, if we have pole at 0, -1 plus j and -1 minus a. So you have two, what you say, poles, conjugate poles, and you have one pole at origin. So this one pole at origin will define your steady state error, and -1 plus j and -1 minus j will define your transient response. Is this clear? Okay, so for third week course, uh, like you have gone through, I think I'll just review this whole thing so that you can recall all those concepts, and if you have any doubt you can ask. Then we'll conclude the session and we'll meet next time. So first of all, we started with this, we said that okay, any physical system, and then we want to model that system mathematically. So we saw this integral differential equations and all. Then we said that okay, these are integral ODEs and all. So it is difficult to solve and get the solution. So what we'll do, that we'll simplify this. So we'll have a transformation, mathematical transformation. And for that, since most of the physical system has this exponential, like a damped response and sinusoidal response. So we said that, okay, we'll have a Laplace transform. We'll transform this time domain equation in Laplace domain, and we'll do the analysis. So what happens that this differential equation ODs that get converted into algebraic expression, and we simplify all these things, and we have this transfer function thing in Laplace domain. So simply, if yt is a convolution of input and the impulse response of a system, that is, if we say ht is impulse response, so yt is equal to integration x tau ht minus tau, tau going from minus infinity to infinity if this is a non-causal system, otherwise it's 0 to infinity. So this kind of thing can be simply transformed in Laplace transform is ys equal to xs into gs, or we can say hs, like that. So now we have transfer function. We saw like how can we, from blocks and all, we can model this thing. So for doing the analysis, if we have complex system, we uh, uh, it is depicted that, okay, we have some techniques from which for complex system also we can try to find the transfer function, because for simple configuration we can do, like for cascade or parallel, or we can say the feedback. But for more complex, we do the some simplification. So like block reduction technique, which is one. So here we have different blocks, and we try to introduce how to move a takeoff point or summing point, or how can we uh, like modify the blocks and all. And then we saw that, okay, for complex system, if we do this, there may be some, if we do some mistake, then it will be difficult to debug and all. So what we'll do, we'll have a simple formula, which is Mason's gain formula. We'll plot a signal flow graph, and we'll simplify the transfer function. We simplifying the transfer function from the signal flow graph only. We don't need to do this reduction and all, and we don't need to go into these things. So we have all those the signal flow graphs and all, and there is this Mason gun formula that is applied to find the transfer function. This is about the signal flow graph. And then once we have transfer function of system, what we are trying to do, we are trying to say, okay, we have the transfer function. Now we want to analyze how the system will behave. Now, since we are studying linear time invariant system, so if we have response to one signal, then we can find response to other signal, because there will be uh, uh, like suppose we have response to impulse signal. So we know any signal can be written as this uh, weighted sum of impulse signal. So if we have a response which is known to impulse signal, then we can find a response to any other signal. So similarly, if we have unit step response, then we can find a response to other signal. So this is a very good property of LTI system, which is not in nonlinear system. So here, and since it is LTI, so once you have found, okay, this is the response, even if you try to find the response to another signal after 10 days or 20 days, years, then also response will be same. It's just because you are performing at that time, so response will be from that time only, but this response is same. So this is about the time domain response. So we know this thing. So for analysis of this response, what we do, we give some sample signals or standard signals like unit step and ramp input or impulse signal, and then we see, okay, this is how the system behaves. So for this, if some input is given, there are two parts of this response. One is transient response, and another one is the steady state response. So transient response is basically the initial, because of when there is no input, and if there is perturbation in the system, you can say, then what the response, it will settle to its equilibrium point. So this is what we saw, that if there is no input, so its response is y0 e to the minus t by tau. So it will die out like that. And then STD state response, or we can say forced response, is someone like some response which happens after transients die out. So if transient doesn't die out, like in oscillatory system, then we don't define steady state or like transient, because these two are mixed, like kind of thing. So we have these two part of response of system. And then we saw that, okay, generally systems are LTI system, we consider two type of system, first order and second order. For first order system, it's simply a delay system with some gain. So that we have found out when we are there is application of this unit step, then there is this tau which characterizes the system. The more the time constant, more delayed the response of the system. And this is what about the first order system. For second order system, we saw, okay, there is oscillatory response and there is this damping term. So like a mass spring damper system or pendulum system, we can say, with aero drag. So all those are this second order system type of thing. I mean, basically we are modeling. We don't know what is the actual system. Like there may be different kind of forces acting, but from our from what we can think, we are saying, okay, there is this mg force which is acting on pendulum, and then there is this aero drag, which is, there may be some other force also, but we don't know. We are saying, okay, these are the approximate force. These are the forces that we can think of that is acting, and we'll model according to this. So we are doing a model of this. If this is behaving good, like as good as the system that we are modeling, then say, okay, that model is good. If not, then we redefine the model like that. So second order system, then again, if unit step is applied, there are different type of defenses responses that is obtained from second order system, and that is based on the two parameters, which is omega n and zeta. So if zeta varies, accordingly the behavior of system varies. So this is what we discussed, this underdamped, overdamped, or critically damped, all those things. This is all about transient response of the system. Now because it's not only about transient response, when we are trying to like make a control system like such that the plant is following the reference that is being provided, in that case we are also worried about a steady state, that what is the value of the output at a steady, because we want that it should track the reference. So in that case we talk about a steady state error, and we saw that, okay, for different inputs, like these are standard signals, what is the steady state error that we get, like position error constant and velocity error constant, all those things. And yeah, so these are the things that has been taught in week 3. And for week 4, next time we'll deal with some questions on this stability of the system. Okay. So listening, I am previous class. Okay, so PDF is already uploaded. You must have got the link on the website. From there you can get. Anand Teja, I couldn't understand your question. This one, Vivo stability for. Or busy with other thing. Anyway, so I think you are able to understand all the things, like all the question that we have solved. Fine, then we'll conclude this session. Thank you all. You can leave now. Thank you.